You know how a tiny chip in your car's windshield can suddenly turn into a giant sprawling crack? Or why a brand new metal part might just snap when you least expect it? Well, the answer is often a hidden danger that engineers are frankly obsessed with. It's called stress concentration. And today, we're going to pull back the curtain on this critical concept that shapes pretty much everything around us. And this is the crazy part. Sometimes the absolute smallest detail, a corner that's a little too sharp, a single hole in the wrong place, can lead to a complete system-wide catastrophic failure. We're talking about invisible forces powerful enough to take down airplanes and tear ships into. So what is this invisible force? Is it some kind of dark magic? Nope, it's pure physics. It's all about how internal forces, what we call stress, flow through an object. And when that flow gets messed up, the consequences can be, well, disastrous. And unfortunately, history is full of examples. And when you look back, the pattern is just wild. The Havilland Comet, the world's very first commercial jetliner, literally fell apart in the sky because of tiny cracks that started at its square windows. During World War II, a whole series of ships called Liberty ships, which were built super fast for the war, just split in half in the cold ocean. And what connects all these tragedies? The exact same hidden culprit. Okay, to really get why this stuff happens, we have to zoom in and enter the hidden world of stress. The easiest way to think about it is to picture stress as an invisible river of force flowing through a material. Now, in a perfect, smooth object, that river flows evenly. But here's the thing. Nothing in the real world is perfect. The moment you introduce any kind of irregularity, a hole, a sharp corner, even a surface scratch, you've just thrown a giant rock into that smooth flowing river. The flow can't just stop, so it has to crowd together and rush around the obstacle. It concentrates in that one tiny area, creating an incredibly dangerous weak spot. This image is the perfect way to visualize it. Think of those lines as the current in our river of stress. When the river hits that hole in the middle, the current has to squeeze around the edges, right? It speeds up, it gets more intense. That is exactly what stress does. The force lines get packed together, and the stress right at the edge of that hole becomes way, way higher than anywhere else. And you already know this. You do it all the time without even thinking about it. If you want to tear a piece of paper, what do? You make a tiny little starter rip, right? Well, that little notch is a stress concentrator. You're basically creating a weak point on purpose to make the rest of the tear effortless. You're a physicist and you didn't even know it. Now, intuition is great, but engineers can't just, wing it when a bridge or an airplane is on the line. They need to put a number on the risk. They need to measure exactly how dangerous a specific corner or hole is. And for that, they have this incredibly powerful little tool called the stress concentration factor, or just KT. The best way to think of KT is just as a simple risk multiplier. It's a single number that tells you, hey, the stress right here at this point is X times higher than the average stress everywhere else. It's a quick back-of-the-envelope way to see how much trouble a design feature might be. So let's break that down. You've got your nominal stress, that's the overall average load the whole part is feeling, kind of the baseline. But then you have the peak stress. That's the one you got to watch out for. That's the super high, localized stress right at the tip of a crack or the edge of a hole. And KT? Well, KT is the number that connects the baseline to the peak. And check this out. This is like the classic example every engineer learns on day one. If you just take a flat plate and drill a simple round hole in it, bam, you have instantly tripled the stress right at the edges of that hole. The material in that one tiny spot is now working 3 times harder than the rest of the plate. This is why KT isn't just an academic number. It's absolutely crucial. But wait a second. A high KT value doesn't always mean instant failure. The final outcome really depends on what the thing is made of. The same stress hotspot will affect a piece of steel totally differently than it affects a piece of glass, which brings us to this critical difference between ductile and brittle materials. So on one hand, you have ductile materials, like most metals. When they get overloaded in one spot, they can actually stretch and bend just a little bit. They have some give. This basically acts like a tiny built-in safety valve, letting them safely spread that stress out. But brittle materials, think glass, ceramics, some plastics, they have no safety valve. They're rigid. When they hit their limit at a stress point, they don't bend, they just snap. Game over. And this photo is a perfect, sobering example. We're looking at concrete, a classic brittle material. See that sharp 90-degree corner? That's a textbook stress concentrator. All the internal forces just piled up right there until one day the concrete just couldn't take it anymore and that crack formed, shooting right out from that corner with zero warning. So you're probably thinking, if these sharp corners and holes are so dangerous, how in the world do we build anything? That's a great question. The answer isn't to avoid them, because a lot of the time you can't. The real key is to design with them in mind, to intelligently manage that flow of stress. Engineers have a pretty methodical way of doing this. First, you play detective. You hunt down all the potential trouble spots on a design, every hole, every sharp corner. Then you analyze the risk. But the final step, that's where the real design magic happens. You actively reshape those features to create a smoother, gentler path for the stress to follow. In the real world, this means trading sharp corners for nice, rounded curves, which we call fillets. It means rounding off sharp notches. You avoid any sudden changes in shape. Every single one of these strategies is about one thing: giving that flowing river of stress a nice, smooth on-ramp instead of forcing it to make a hard right turn.
Okay, now this is my absolute favorite engineering trick, and it's totally mind-bending. The very tip of a crack is basically an infinitely sharp stress concentrator. It's the worst-case scenario. So how do you stop that crack from spreading? You go to the very end of it, and you drill a hole. I know, it sounds insane, but you are replacing that infinitely sharp point with a much larger, rounder radius, which is way less of a stress concentrator. It's like engineering jujitsu.
Ultimately, this all comes back to a fundamental truth about engineering. It's not about trying to create a perfect world where there are no stresses or sharp corners. It's about navigating the imperfections of the real world safely and efficiently. Because at the end of the day, stress concentrators are everywhere. They have to be. You need holes for bolts. You need corners to make shapes. A great engineer isn't someone who gets rid of all of them. A great engineer is someone who understands them, puts a number on the risk, and then makes smart trade-offs to build something that's strong, affordable, and most importantly, safe. So now you're in on the secret, and you won't be able to unsee it. You'll start spotting these hidden danger zones everywhere you look. You now understand the invisible forces that are either holding our world together or trying to tear it apart. The hidden danger is now visible. So the real question is, what are you going to do with that knowledge?